Okay, next I'd like to cover yet another distribution function, and that one's going to be Poisson distribution functions. So first of all, when do you use Poisson distribution functions? Well, they're usually used for counting experiments. So in physics, the easiest one to describe of those would be, of course, radioactivity, where you're counting up the number of decays in a given time interval. And that's the example that I'm going to use here later in this lecture. So a Poisson function is just another example of a distribution function. It's like a Gaussian function with a tail. It's kind of skewed. It's not symmetric. It's got a long tail off to one side. And depending on what the values are, it might be slightly truncated, and I'll show you examples of that in just a second. So here's what the Poisson distribution function looks like. E to the minus mu times mu to the nu over nu factorial. So here, mu is the average number of counts for a given time interval, and nu is the actual number that you count in a particular time interval. So just like any other distribution function, the Poisson function obeys the normalization condition, which means that if you add up over all values of nu, that you've got to have a probability of 1. To remind you, we talked about this back in, I think, Chapter 3. If you have a counting experiment, remember that the uncertainty in a counting experiment is the square root of the number of counts. So, for example, for a given time interval, nu, your uncertainty would be the root of nu. And for your average value, mu, the uncertainty on that average would be the square root of mu. Okay, so those are your uncertainties. So I've got a maple file showing you what the Poisson distribution function looks like for various values. So here we go with that. What I've got here is a value where the average value is a half. So mu is 0.5. And then what I've got is I've inputted my Poisson distribution function, okay? And so that's e to the minus a half times 0.5 to the x power divided by x factorial, and then I'm plotting my Poisson function as a function of x. Okay, so if your average value is a half, then you can expect your Poisson function to look like this. It starts off, you can see it kind of looks like a Gaussian function that got chopped off, and we're only showing the last part, and it has the tail. Now, as you increase your value of mu up from a half to something larger, then more and more of that Gaussian function is going to start to appear. So here it is at mu is equal to 1. Okay, and you can see that it looks like it's kind of coming out there. And then at mu is equal to 2, you see even more of your function kind of appearing. At mu is equal to 3, even more of it appears, until as mu gets very, very large, here I've got, let's see, mu is equal to 10, it's really hard to tell the difference between a regular Gaussian distribution function and a Poisson distribution function. And the only difference that you can see is, like I said, it's slightly skewed and you have a little bit more of a tail on this right-hand side. Okay, so Poisson distribution functions approach Gaussian distribution functions for large values of mu. Okay, I wanted to do another example problem for you. Here I'm talking about radioactivity, so you have a radioactive sample with 5 times 10 to the 19th atoms in it. And each of those atoms has a probability of 3 times 10 to the minus 20 of decaying in a given 5-second time interval. So what's the expected average number of decays from the sample in 5 seconds? And then they want you to compute the probability of observing 0, 1, 2, and 3 decays in a given 5-second interval, and then also the probability of observing 4 or more decays in a given 5-second interval. Okay? So the solution of this problem, to find the average number of decays, all you have to do is multiply the probability times the total number of atoms. So the probability will basically just tell you how many decays are going to appear in that 5-second interval. So here you've got 3 times 10 to the minus 20 decays per 5 seconds times the number of atoms, which gives you an average number of 1.5 decays in that sample in a given 5 seconds for that particular size of sample. Because any given one atom has a probability of 3 times 10 to the minus 20 of decaying. Hopefully that's clear. Now it asks you to compute the probability that you've got 0 decays, 1 decay, 2 decay, 3 decays in a given 5-second interval. So for that we use our Poisson distribution function. So here we have e to the minus mu, mu to the nu over nu factorial. Our value of mu we already computed, it's 1.5. And then we're going to plug in the values 0, 1, 2, and 3 into that formula. So here I've written out what it is, for example, for nu equal to 0. It would be e to the minus 1.5 times 1.5 to the 0 power over 0 factorial, and that would give you a value of 0.223. Okay? If you do it also for 1, 2, and 3, I've listed out, I haven't bothered to show it because it's the exact same idea, it's just plug and chug. I've listed out what those probabilities are. So 0.223, 0.335, 0.251, and 0.125 for nu equal to 0, 1, 2, and 3 respectively. Okay, so that's part B. And then it asks you the normalization condition. Using the normalization condition, we can figure out what the probability of 4 or more decays is. Because of the normalization condition, we know that the total probability has to be 1. Okay, so for 4 or more decays, all we would do is add up the probabilities for 0 to 3 decays and then do 1 minus that number, and that would give us the probability for 4 or more decays, and that's 0.066. So there's a 6.6% chance that you'll see 4 or more decays in a given 5-second interval. Okay, and that's pretty much it for the Poisson distribution function. So see you in class.